In this video, we are going to learn how to build a logistic regression model in SAS. If you know what logistic regression is, you must be knowing that logistic regression is a type of regression model which is used for categorical dependent variable. This is very popular in cases where the dependent variable has got only two values, or technically speaking, the dependent variable is binary in nature. Well, it's used in many industrial and academic applications. One of the most important use of logistic regression is in the field of credit scoring, which is used by most banks and financial organizations. So we will learn how to quickly build a logistic regression in step by step. So I'll take an example and that's how we're going to learn. So here is an example. We're going to data which is having the student's performance and whether a student is getting admission in a college. Okay, so the dependent variable for us is this one, the one I have highlighted. It's admit. The students have applied to different universities, and whether a particular student get admission in the university depends on various factors. The factors could be his GRE score, his GPA score, the rank of the university, the undergrad university which the student attended. So these are some of the factors that could affect the student's admission to a particular university. Right? So we'll try to predict if a student is going to get admission in a particular university or not based on his GRE score, GPA score, and the rank of the university that he attended for his undergrad education. You can see that the dependent variable has got only two values, 0 and 1. So if he gets admission, we have said it that we have denoted it as 1. If it doesn't get admission, we have denoted it as 0. So that's just a denotion. You can actually put any value. You can put 1 for admission, 2 for not getting admission. It's entirely up to you to use any notation that you are comfortable with. So the idea here is to find out what is the probability that a student is going to get admission in a university. And as you know, to model for probability of an event or probability of happening something, logistic regression is probably one of the most popular modeling algorithm used. So the first thing we have done is we have just imported the data from my desktop, and so first let's try to run proc content, where you'll get to know what exactly is there in the data. So it's going to give us how many observations are there in the data. We have got 400 observations. There are 6 variables, but we are going to use 4 of them. Yes, the variables are admission. This is going to be the dependent variable for us. GPA score, GRE score, and rank. These 3 variables are going to be the independent variables. Now the last 2 are the ones we have created. So we'll make use of them later on, but not in the beginning part of in the first part of this session. Okay. Let's try to understand in the data how many of them have got admission. So we'll use a proc frequency for that. So in the data, we have 127 students who have been able to secure an admission in the university, and 273 who haven't been able to get admission. Now remember, this is the data that we have with us, for which we know for sure that whether a student has got admission or not. But the model will not be used for this data. The model will be used for a completely new student for whom we have not actually the value of his admission, or we do not know actually whether the student is going to get admission or not. We'll predict the probability of him getting admission using this model. So that's the idea. So this is just a historical data, or the data that we already know, or the outcome of the model is already known to us. Okay, so these people have already got admission, so we know for them. So we have got some sort of a value for the dependent variable. Okay, so we call this data as a training data. Okay, little more analysis on the data. You should actually do more analysis. I'm going to limit it to only means, but you probably should do univariate analysis as well on the data and see whether the data has got outlier, the data has got good distribution of a good distribution for the model to build. Okay, so what we can see is that 31% have got admission. So it's a 31% to 69% distribution for 1 and 0, which is fairly a good distribution. Ensure that the event in this case is 1, because we are interested in getting admission and we have denoted it as 1. So ensure that the percentage of 1 should be sufficient enough, at least 2 to 3% or 4%. Anything below that is bit of an issue. Then we have got the independent variable. The average GRE score is 587. The minimum is 115. Sorry, the minimum is 220 and the maximum is 800, and the standard deviation is 115. Now this is one thing that you should remember, that the standard deviation should never be 0. If the standard deviation of an independent variable is 0, then that's a problem. You cannot use that data or use that variable in the model building process. Why is that so? Because if the standard deviation is 0, which means that there is no variation in the independent variable, and that's not a good thing. If there is no variation in the independent variable, it is not going to help you predict your dependent variable. So that's the idea. So all you need to do in this case is just drop that variable from the analysis. So ensure that your standard deviation is always non-zero, and the more it is, the better the variable is for prediction. The GPA score average is 3.3 and its standard deviation is 0.38, which is non-zero, which is good. Rank is anyway is a categorical variable. It's not a continuous variable to say. So mean of rank won't make much sense, but all you need to know what there is a good variation of rank. We have got minimum of 1 and maximum of 4. So for rank variables which are categorical in nature, or variables which have got ordinal in nature, it's always good to do a proc frequency in order to understand the distribution instead of proc means. Okay, so I would encourage you to do a proc frequency of rank in this case. Okay, we can actually do it. Okay, we can actually show it to you whether there is a good distribution of rank. You can see that yes, 15% of people have come from rank 1 university, 37 from rank 2. So pretty good distribution. So it's a useful variable, so to say. Okay, let's straight away go to building a model. Now remember one thing, in real scenarios, there are many things that you do before you actually go ahead with the modeling. But here the purpose of this tutorial is to make you familiar with the basic logistic regression and how you interpret a logistic regression and how we use a logistic regression in practice. But you actually do a lot more before you get into a modeling process. The steps could be analyzing your data, removing some of the observation, finding out which independent variables are good enough, dividing your data into training and test sample, or training a validation sample. So that's another important thing. Build a model in training sample and test your model in validation sample. So these are some of the exercises you do. You do sampling as well. You find out a best sample which would represent your population, and many more things. But we will only limit to understanding a logistic regression without going into the details of the other things that you actually do before building model. We'll see that in another tutorial. So we'll use the student data. The syntax is like this: procs logistic data, and then you provide the name of the dataset, and then you provide what is known as DESC. DESC. It's a keyword you use because by default proc logistic model for 0, but we are interested in 1 in this case, right? We are interested that if a student is going to get admission, now 1 is the is the value of interest in independent variable. And what it does, proc logistic always takes the ascending order. That means it will always model for the lowest value among the values in the dependent variable. So the values are 0 and 1 in the dependent variable. So if you do not use DESC descending, then it is going to it is going to build a model for 0, probability of getting 0, not 1, but we are interested in 1. So always use descending if you are interested in finding probability of 1. Okay, so we are talking about 1 and 0 in the dependent variable, so don't confuse with that. Alright, so we are also using class statement in this case because rank is sort of a categorical variable which has got 3 categories. So we want that these categories should be taken into consideration, and we are saying that rank is a categorical variable which has got 3 ranks. So we'll get 3 estimates for the variable rank in this case. If you do not use that, you won't get 3 estimates. You will just get 1 estimate for for rank. It is going to be considered as a continuous variable, which is not the case, right? So it's always good to use the class statement if you have a categorical variable in place. The model statement is like this. And this is the most important and something that, you cannot have a class statement, that's okay, but you should always have a model statement. That's where you define your model. So left hand side you put your dependent variable admit and then equal to, and in the right hand side put all the independent variable that you are interested in. Now you may not be interested in all the independent variables that you have in your dataset, but in this particular example we are using all the independent variables we have in the dataset. So we are not dropping any one of them, but we might do that when you actually run the model and see some of these variables are not good enough for the model. We'll see that later. There are a few more things we will also mention here. So once we have the model in place, we want to save the probability against each one of these observations in a data set, and we are calling that data set as out data, and you can give any other name. Okay, up to you. So what we want to save? We want to save probability, and we just give that as a name, predict under probability. We also want the lower and the upper limit of that probability. Now in any statistical estimation you always get a lower and upper limit, right? That's the confidence interval for you. So we also want that to have just to understand how the probability is distributed within its lower and upper limit. So we're all ready. We are all set. We'll just run this code. Alright. So next thing that we'll do is, we have the output from the logistic regression. The next thing that we're going to do, we'll just understand each one of these steps. There are many things that SAS will provide you, but we'll go through only the most important ones. Okay. Initially you will have which optimization technique has been used. I mean, there are some default techniques that SAS uses. If you want to specify any technique, then you can specify. But normally you will find that most optimization techniques are going to give you pretty much the same model. There will be hardly any changes. So you need not worry that. So here we SAS has used Fisher scoring, which is by default is used. So number of observations rate and use both 400 and 400. Now this is important. What happens is that sometimes your data has missing value. If one of the data point in any one of these variables, dependent or independent, is missing, then the entire row will be deleted, or the entire row will not be used for the estimation, or that particular row will be completely ignored. So if you have data with missing values, your number of observations used will be less, that very less number from the number of observation rate. But in our case, we do not have missing data, so all the data that we have provided is being used for estimation. Then we have response profile, wherein you have the categories. In logistic regression, you always have two categories. We have denoted at 1 and 0, and there is sufficient distribution, a good distribution rather, for it to estimates for the probability of getting 1. Now we are interested in probability model admit equal to 1. So what is the probability that a student will get admission in university? So we are interested in probability admit equal to 1, and that's exactly what is the output giving us. Now remember the DSE statement that you had I talked about for a while. If you do not use that, here it is going to be admit equal to 0, but we are interested in 1, right? We are not interested in somebody not getting admission. We are interested in somebody getting admission. So ensure that you use the statement DSE in the proc logistic. Then make sure always see the model convergence status. Many times you do not get a converse model. If a model is not converged, or it doesn't converge, then you cannot use the model output. You will get some sort of a model output, but that won't be the optimal model output. So you have to go back and do a lot of other things before you can actually get it to get the optimization routine to converge. In this case, the model conversion criteria is satisfied, so we are fine with, and we should be having an okay model, or rather the model that we are getting can be used. The next table you get is model fit statistics. The three important statistics that you get: one is AIC, known as Akaike Information Criteria. The second one is quasi-Bayesian criteria, SBC, and third one is the log likelihood value. Okay. So the idea here is that you should, I won't get into the details of what this, what the statistics are. You can always learn what is Akaike information criteria, what is quasi-Bayesian criteria, but make sure that if you have multiple models, make sure that the one with less AIC, SBC, or log likelihood value is your best model. Now the idea here is that if you use too many independent variables, you will probably get a good model, but your AIC value and SC value will go up. So having too many independent variables is not considered to be good for the model. The model will be overfit. The model cannot be used efficiently for future data. Hence, AIC SC penalizes you for that, penalizes you for having more number of independent variables, and hence your AIC and SBC value will go up when you use more number of independent variables. So that's one statistic you look at. If you have multiple models, just compare them and see which one of these model is giving least AIC, and that's exactly is the good model that you should go ahead with. The next one is the global null hypothesis. Now this is a null hypothesis which is like all the beta parameters in your logistic regression are 0. The alternative hypothesis to this null hypothesis is that at least one of the beta parameter is non-zero. Now intuitively, what does it mean? Well, it means that the independent variables used in this model are able to provide you better results than a random guess. Okay, so it says that independent variables are of some use, they cannot be ignored. Okay, if this is not true, then there is no need to go below. If your null hypothesis is not rejected in this case, or rather in other words, if the statistic likelihood ratio test, score test, or wall statistics, they are not all significant. In this case, we have all all the statistics are significant because the values are less than 0.05. You can see the p values. The p value for likelihood ratio test is less than 0.05. Same with score stat, same with the wall statistics. If this is not less than 0.05, your global null hypothesis will be accepted. That means all betas are 0. So there is no point in building a model, rather going ahead with other statistics. You have to stop, go back and rebuild the model again, because it says that none of the independent variables are good enough for the to predict your dependent variable. But luckily we have all three statistics significant, so we are good. The next important and the most important is the analysis of maximum likelihood estimates. The algorithm used to find out the estimates in logistic regression is maximum likelihood estimation algorithm. Hence, we get we call these as maximum likelihood estimates. So, like any linear regression, you get intercept and slope coefficients. The intercept is in this case minus 4.88, and the slope coefficients, there are remember there are 3 independent variables, so we will get as many slope coefficients. However, one of the independent variable is a class variable. Okay, so if it's a class variable, you would get that many number of additional how many number of classes are there? 3. So we'll get 2 more estimates. So if there are n classes, you'll get n minus 1 more estimates, and we'll see why is it so. For GRE, we have got the estimate as 0.00226. For GPA, it's 0.8. For rank 1, it's 0.89, for rank 2, 0.21, for rank 3, minus 0.44. What is important to see here is the p-value of all the statistics. Now ensure that for the p-value to be significant at 95 confidence level, it has to be less than 0.05. Here it is the case, it's less than 0.05, so significant. Less than 0.05, GPA is also significant. Rank 1 is also significant. Rank 2 is not significant, and rank 3 estimate is significant. So we are interested only in the cases where the variables or the estimates are significant. Insignificants are always going to be ignored because they are not significant. All right, the next important thing to look at in the output of logistic regression is whether the model is able to do a good job or there can be a better model. So we'll look at what is known as association of predicted probabilities and observed responses. So here what is important to look at is the percentage confidence and percentage discordant. So if you have higher percentage of confidence, the better is the model. Okay, and what we usually look at is the C value, which is also known as the concordance statistics or C statistics. It is 0.693 in this case. A few things to remember about the C statistics. The C statistics has to be greater than zero point 0.5 all the times. It cannot be less than 0.5. If it is, then your model is totally wrong. It performs very bad. Why? Because in a binary response variable, if you toss a coin or you randomly choose, you will most likely get 50% of the times correct. So if your model is doing worse than that, then your model is worse than even random guess. So your model has to be greater than 0.5 to be called a good model. But and concordance statistics, C statistics always normally lies between zero point 0.5 to 1. The closer it is to 1, the better is the model. So getting a bigger or higher C statistic is always good. So in our case it's 0.69. So we might do something with the model to get a better C value. Some of the ways are including new variables, include transform variables, doing the including polynomial terms of the variables, and see if the C statistic is going off. If it is going off, then the model is able to do a better job, and the one with highest C statistics should be the one that should be used as the final model. Okay, now we have saved the output in the out data. So let's go to the work folder, and that's exactly where I have saved. But you can save it in any place. You can save in your own folder as well. So in the output, we have the estimated probability, lower confidence, and the upper confidence. Okay, this is estimated probability. So against each and every observation in the training data, you have a probability. Now, what we would be expecting is that wherever we have admit equal to 0, the probability should be less than 0.5, because that's the middle probability, right? Anything greater than that, we should have a 1. Anything less than that should have a 0. If that's happening, then that's a good thing. Otherwise, it's something is wrong, or rather inefficient. So here it is right. Admit it 0 and probability is less than 0.5. But it gets wrong in the second one, because the probability of admission is 0.2, but the person gets admitted. So that's a wrong prediction. And it can happen. In model, you cannot get right all the times. The next is the probability of getting admission is 0.73, which is greater than 0.5. So your probability chances are that the student will get admission. That's what the model says. And you can see that yes, the student has got admission. So it is a correct prediction. So there will be correct prediction, wrong prediction. You can actually do a tabulation and see how many times you are getting correct prediction and how many times you are getting wrong prediction. And we call that as accuracy test. Okay, you can do it by yourself. I'm not going to do it here, but you can test greater than 0.5 and admit equal to 1. How many is there? Less than 0.5 and and admit equal to 0. How many are there? So that's your correct prediction, and rest everything else is just a wrong prediction. And just see what is the percentage of correct prediction and what is the percentage of wrong prediction. And the objective should be to increase the correct prediction. All right. Now the next thing. Now the important question, and many students have asked me this question, that all right, you have the model in place. Now the model is able to give you the probability value, but how do you use it? Well, the model that we have just seen here. So model is nothing but just equation, right? So if you're familiar with the logistic regression equation, it is just a logarithm of p by 1 minus p equal to beta naught plus beta 1 x, where x could take many independent variables, and you have got the estimates. Just put the estimates and you will find the probability value. And that's exactly how SAS has been able to find out the probability for each observation. You can do it by yourself also. And I'll encourage you, write the logistic regression equation, put the estimates value, and find the probability value. You can find it by yourself also. Now, for a completely new student, for whom you know the GRE score, GPA score, and rank, just put the values of this, use the estimates, and find the probability. If it is greater than 0.5, predict that the student will get admission. If it is less than 0.5, the student is not going to get admission. Okay, and if it is exactly zero point 0.5, then the conclusion is that it's ambiguous. It's not very clear whether the student is going to get admission or not. That's the way you use a model to predict something totally new. Alright, as I've said, you can actually improve this model by including more independent variables. You can use many other statistics if you have the access to the data. It's not just a GRE GPA that matters, it's also the other things, right? That could be let's say the admission is on engineering subjects, so it's the marks on mathematics in undergrad will matter a lot, mathematics or science. Okay, just put that as a variable. The second other thing, among other things, could be score on language subjects. Does that matter in getting admission or not? Extracurricular achievements and so on. So if you have access to more independent variables or more data, just include them. If you do not have, then do transformations of whatever data or whatever independent variables you already have. Just do transformations. So we have done one transformation here. We have just you are using a polynomial terms. We are squaring the GRE and squaring the GPA, and we're calling it as GRE2 and GPA2. You can do any number of transformation, logarithmic transformation, exponential transformation, and so on, as long as you are comfortable with with explaining this variables. So we'll just run this, and we'll include this new independent variables and run the logistic regression again. So what is important here is to see whether okay, make sure that you close the data set. Do not open it and run. That's not going to run. Anyway, we already have that in students, so we can directly run it. So what I was saying is that by including more variables, look at the C statistics. It should go up, but ironically, it has gone down, and it can happen actually. So adding more variables, adding polynomial terms in this case is actually not helping us. In fact, it is reducing the efficiency of the model. So it is better not to use them. Or maybe you can try other transformation like logarithmic transformation, exponential transformation, and so on, and use in the model and see. So you just have to go back and forth and try all your use all your creativity to find a better model. And there is no thumb rule as such what exactly is the best model. Just try all sorts of things. Do transformation, use polynomial terms, use different algorithms, and you will come up with a better model. The second thing that we're going to see is model selection in logistic regression. In logistic regression, you have many ways of selecting a model, and one way is finding out a set of independent variables which are very good for the model. Some of the independent variables are not so good, and they should be dropped out from the model. So there are a number of variable selection statistics, variable selection algorithms that comes along with logistic regression, and it's also there in SAS proc logistic. So one of the way is forward selection. The second one is backward selection, then stepwise and score selection. I won't get into the details of what the selection, how the selection of variables happens, but these are some of the selection that you can use. Okay. in some if I were to tell you in brief what the selections procedures are. The selection procedures take one variable at a time, okay, and see whether that is useful to the model or not. If that is useful, then they retains it. Otherwise, the algorithm is going to drop the variable. So that's the idea. So to the syntax, you just add this one, selection, and you can specify what is the entry criteria and what is the stay criteria. It's entirely up to you, but it's always good to go with the default entry and stay criteria. Selection is forward, it could be backward, stepwise, or scope. So let's go ahead with forward and see what is forward selection and how do we how is a forward selection logistic regression is different from a normal logistic regression. Now you can see there are many steps in which the variables are selected. So this is step 0. Only the intercept is there. Okay. In step 1, only first variable is used. Rank is used. Okay. The second one, and by the way, the most important variable will be entered first. In the step 2, GPA is used. Okay. In step, so you have rank and GPA with the model now. In step 3, GR is entered. So now you have all three variables. Okay. Then when all the important variables are included in the model, then you will get your maximum likelihood estimates. Now there are sometimes what happens is that some of the independent variable do not satisfy the entry criteria. They do not enter into the model because they are not considered to be good enough, using some sort of a statistics, and the statistic used in this case is the chi-square statistic value. If that is the case, you do not quite use that model, that gets dropped. And we have only three variables which all are important ones, so it's all entered in the model. But if you have like 10, 15, 20 variables, some of them will get dropped in the process. You can use a backward also. Backward is just the opposite. It starts with all variables. Okay, sorry. It starts with all variables and it gets it drops one after the other based on the importance of variable. That's right. So it started with all thing, intercept, GRE, GP, rank. Remember, it's exactly the opposite. In forward, it started with just intercept, then GRE, GP. It went one by one. It started with intercept and then one variable, two variable, and then three variables. In this case, it's exactly the opposite. It starts with all three variables and it drops based on exit criteria. But here all three are significant, so it doesn't drop any of the variable. Just finds out the final estimates. Okay, so that's how you can build a logistic regression model. One of the exercises that you can do is use the same data and you can find the data. You can get the data in the description section of this video. You can get the access to this data. You can also get the code that I have used in the description section, and you can use this data. And the exercise that you should be doing is, we have got a C statistics of 0.693. That's the best. Can you increase that? Can you increase with increase to, let's say, 0.72 or 0.73 or so on? Just try all sorts of combinations of independent variable and see if you can increase the predictive power of this model. Thank you so much.